Boa tarde a todos. Hoje nós temos mais um seminário do Departamento de Ciências Atmosféricas do IAG USP, e hoje nós temos o prazer de ter como convidado o Kevin Basoa. Ele é do Centro de Ciências do Clima e la Resiliencia do Chile. Ele vai falar sobre boa tarde a todos. Hoje nós temos o seminário do Kevin, ele vai falar sobre dispersão de aerossol e black carbon no Chile, né? Ele vai falar especificamente do inverno e verão de 2016. I would like to thank the Kevin for accepting to give this presentation. And now, Kevin, you can start your presentation.
Okay. I'm going to share my screen. I think you should be able to see my presentation now.
It's okay.
Okay, great. Thank you for having me. It's a pleasure to present our work in this seminar. I'm going to just clarify this is an ongoing work. It's not finished, but we have a lot of results that that some of them are showing this presentation. So here we go. Like Rosemary said, this is a work for that's called aerosol and black carbon dispersion in central and southern Chile in winter and summer from 2016. Now the contents of this presentation. Well, we have this the problem at hand that we are treating, how we are treating this problem. Some summary of the model configuration that we use to our simulations, the evaluation of the meteorological field that we use, then the result on the concentration of PM2.5, and some summary of all the presentation and the discussions. Just a brief context. Here in Chile, we have a lot of problem in the southern part of Chile. We have a lot of problem of air quality in regarding the levels of PM2.5. Here you can see some photograph of the southern part of Chile, in which the energy poverty makes the people to use a lot of fuel to warm their house. We have a lot of issues with that. Next, we start on this, and Chile has international committed in the NDC, this national determined contribution. That is one of the commitment is to reduce at least by 25% the emission of black carbon from 2016 to 2030. This is one commitment that Chile submit in this NDC, and to this study in the 2016, we have this share of sectors that is contributing to the black carbon emissions. Here you can see that the more important sector are the residential sector, that is account with emissions coming from the use of fuel to different activities, but majorly used for heating household. And the second sector is the off-road machinery that accounts for 27%, more or less, for total emissions. So this is important because in this, as Chile has a commitment to reduce their emission from a base year, you can say, it is important to know the right amount or have less uncertainties on the base year. So I'm going to talk about how this compromise is has been done. In this work, I was part of them. We use we calculate some national inventory and projection for raw carbon that comes from different scenarios for energy demand and for different sectors. These are sectors that account for different energy consumption. You have the CPR that is account for commercial, public, and residential, the industry sector, mining, transport, and electricity generation. So we take all these energy demands and apply some different emission factor. Most of them come from this EMEP and EEA guidelines for inventories, but we have other emission factor for different activities. There is a lot of disaggregation in this work, but here we are showing this the final result. No, that is what interests us. And here these are the final trajectories or scenarios for black carbon that we have. So Chile based his compromise based on these numbers. So it is important to address if these are the right number or if they are close to the right number. So like I said, this number have a big uncertainty. Here is an example of that, where you have different emission factor from different studies for wood burning. As you can see, there are go from I would say 1 to almost 80. So you have a lot of dispersion in the amount of emission coming from wood burning. So in a way, you can say that you don't know exactly how much emission are coming from wood burning. So for the case of the Chile and DC, we use this emission factor, and with that we can account that residential emissions account for almost 40% of the national emissions. But as I said before, there is a lot of uncertainty with this value, so we need to constrain the emissions level from PM2.5 and so on, the BC emissions. So in this case, we are considering the BC emission a fraction of PM2.5. So we are focusing our work in the PM2.5 emission, and then the fraction that accounts for BC emission. So we talk a lot about PM2.5. So how we are constraining that, and this is the approach that we are taking. So we have the emissions fields and the weather field, in this case from WRF, for these several pollutants. We put these two input in this EMEP model, the chemical transport model. You can see here the reference where you can find a lot of the description of the model. The model is nested in CAMS, BC, and EC, the boundary and condition and initial conditions taken from CAMS. Then we have the pollutant dispersion in surface and in 3D output, and also we have the AAOD. There is several other outputs. Well, this is a summary of them. Then if we have the output of the model, then we calibrate the model considering the simulation and the observation. We have a large network of monitoring station in Chile. Also, we are considering the AERONET network, and also we have some BC black carbon observation in some part of Chile. Then when we calibrate and see our result, we change the emission level according to this result. So basically, that is the approach that we are taking in this research. Just a little bit of what the model is saying about the aerosol, or how the aerosol are represented in the model. This is a very summary of that, how the model represents the aerosol. Here you can see this circle is you can imagine that there is a particle that is part of several other pollutants, where you have secondary inorganic aerosol, primary aerosol, biogenic secondary aerosol, mineral dust, sea salt, and other anthropogenic secondary aerosol. So for the part of the upper part, you have all the anthropogenic emission, where you have the industry, transportation, agricultural activities, and some other mobile sources like of raw machinery. For the biogenic emission, you have some from forest, for example. You have mineral dust that is transported like from the desert, and sea salt coming from the waves in the sea. Also, the particles are considering a part of water, of humidity that is part of the aerosol. For the part of BC is part of the primary aerosol. So in the model, you have that in the primary aerosol that you put in the model is separated in fractions, depending on the sector of emission. This is SNAP sector, that is a selected nomenclature for air pollutant. You have that sector, and the range of how much BC is in the emission vary depending on the activities. Here you have an example that can be 5 or 45%. And another thing, the model consider consider EC concentration, but in this case we are assuming that EC is equivalent to BC, so that is the approach that we are taking. Now I'm going to go back to the calibration, that is the evaluation methodology that we are using. So we have the calibration that we are doing against PM2.5 concentration. Other pollutants we are considering too. Basically, we consider the pollutant that we have observation to compare. It is not more than that. Then we have this concentration coming from the model. We compare this simulation to the observation within the grid. This is an example that how we are doing this comparison. We have here an example of a grid. You have inside the grid an observation, and we compare the values of this grid to this point. And if we have several observations in the same grid, we take a median value from all the observations. That is the best way to compare this the simulation against the observation. Regarding the observation, this map shows in the red dot, we can see where are these points of observation in Chile. There is a lot of observation, but here I show the monitoring station that have values to that have observation to compare. So for the black carbon validation, we have a few observations, and we are using an approach taking into account the BC fraction in the PM2.5. Like I said, we have a few observations of BC, and there are all in the capital of Chile, Santiago. So we have this like issue with the validation of BC. So keep going with the configuration and inputs for this simulation. We are simulated 2 periods, summer and winter. In this case, 1 month is February and July. That is not February, it's January. I'm sorry for that. but we have January and July for 2016. We consider 5 days of a spin up. We are thinking on taking more days, but in this case, it should be okay with 5 days. Also, we are considering 36 vertical levels, and the emission cycles we adapted to the Chilean case. There are a lot of more details on the configuration, but this is a summary that can explain part of the result. For the inputs, we have the meteorology, like I said, is work fields. We have 3-year simulation, but we are only using 2 months. In this case, the WRF have a 10x10 kilometer resolution, and the domain considered is from 30 south to 50 south, more or less. And you can see how covers a lot of central Chile and part of the southern Chile. Regarding the emissions, we are combining 2 emissions inventory, one a national inventory gridded at 1 per 1 kilometer, and that is shown here at the right. This is the emission coming from the Alamos, and also we are using a global inventory, HTAB in this case. And here is an example of this national inventory that have 1 per 1 kilometer resolution, and you can see how the emissions in this case for PM2.5 are in. I can say that, but the emissions are in where the people live, so they are related to the population. So this table summarizes where what pollutant we are considering, and from what inventory we are taking. So for the 3 first SNAP sector, we are taking the PM2.5, and CO, and NOx, SOx, box, NH, and ammonia from this Alamo inventory, and also we are taking the road transport. But for the global inventory, we are taking this mobile source that accounts for shipping emission, and also the ammonia emissions from agriculture. We also take this DMS emission from this oceanic emission inventory from Gaia. The other sector were not included. Maybe this could be this could be a problem, but the other sector are not much relevant in Chile, so it should be okay with only these sectors. So this obviously I don't want to check all the details, but here are the amount of emissions coming from this national inventory. Here this is an important one, the PM2.5 emission, where you can see almost all the emissions come from the residential sector. This is what we can expect from that, but we don't know exactly how much is the emission. So this is the work is treating that problem, and also you can see the other pollutants that also have an important participation of the residential, like CO, volatile organic compounds, and ammonia too. So for the part of these are we are passing now from the result. Now the meteorological field evaluation. Here we have 3 different comparison with considering the model and the observation. The model is in the black line, and the observation are in the blue line. This is the same nomenclature for all the other graphics, so keep that in mind. The black one is the model, and the blue one is the observation. So in this case, we have 3 different comparison. We have a lot of more of comparison, but here I wanted to show 3 different locations that are widely separate. So we have like in the north part, in the central part, and the south part of the domain. As you can see, the model is capable to reproduce this daily variable, this daily variability of the temperature in almost all the cases. But as you go to the south, the model tends to underestimate the temperature. And that's one example for the summer. And here we have an example from the winter period at the same location. And even you have a lot of noise in some parts, but the model is still capable to reproduce the variability of the daily cycle that we were interested and even this like weird trends, the model is also capable to reproduce that. And you have to keep that in mind that we have we are comparing we were comparing a point in the grid. So the grid is 10 per 10 kilometers. So it should not be. We can't ask for a model to reproduce the exact variability, but this is okay for considering the grid in the simulation. So for the other variable that we consider to compare is the relative humidity. Here we have daily values. Then you can see how in the summer we have an urban location and a rural location, in which we can see a good agreement in the urban location, but in the rural location, the model overestimate the percentage of relative humidity. And for the winter period, we have the same. The model is capable to reproduce like the amount of the relative humidity, but in some cases it can follow the observation. But as I said before, there is a coarse grid of 10 per 10 kilometers, so these results are okay. Another comparison that we do is the circulation and what we are expecting that the model do. In Chile, we have this upslope and downslope circulation. That is upslope in the day and downslope in the noon of night, and the model is capable to capture this. If you notice that, if you notice this arrow that showing the wind direction, you can see that in the day the wind is coming from the west, and in the noon is coming from the east. No, that is correct. That the model is doing fine this. And for the winter period, we have the same example. The model is capturing the both circulation in summer and winter. Then we have now the concentration fields. Now that we are that we validate the meteorological field, now we have the concentration field. There are two GIF that shows 2 days of simulation with hourly values for 2 days in summer and winter, and you cannot see a lot of detail in that, but you can see the importance of the seasonality. You can see that in the summer the concentrations are way too more low concentration in the summer, and in the winter we have a big big problem in air pollution. So even if this is a simulation, this is what we can see, and you can see, and you are going to see in the comparison with the observation. So this is part of the results. Now we have this big domain that accounts for no, 2,000 kilometers, I think, and that is a lot of terrain that we have to analyze. So we separate this in three parts, in like a north domain, a central domain, and a south domain. So these three domains, or these three parts of the domain, have different in terms of emission and also meteorology. But here I can do a brief summary of what are the characteristics of this each part. For the A domain, we have most urban population. So this is a sector that is domain with urban sources. We have a strong participation of transportation, and a strong participation from the industrial sector, mostly for CO2 emissions, SO2 emission. And also we have a residential sector, but in a mid-level participation. And other sources are not that important in this part. For the B part of the domain, we have mixed sources coming from urban and rural population. In this case, we have low participation on the transport, low on the industrial, and a strong participation on the residential sector. For the last, for the C part of the domain, we have mostly rural population. So we have a lot of rural sources where the transportation is very low, the industrial also very low. But this is an important one, that we have a strong participation on the residential sector, that is mainly due to this wood burning from house heating. Here I have to I wanted to make a clarification. We have these dots are several monitoring station, but this part of the domain accounts mostly for monitoring station that measure SO2 for these thermal power plants and this smelter from copper. So these are not part of this result, but we can use it for calibrate the runs, but they are not showing this in this presentation. So here we now we are seeing the first part of the domain, the north part, and I take an example from three points of comparison, and one in the Valparaiso zone, and the second in Santiago, and the other more to the south. And as you can see, the model is underestimating the concentration, or has a negative bias in this case in the three locations. The same happens in winter. The previous one was in summer, and you can see the same happens in winter, like I said, where in all the cases the model is underestimating the concentrations. Now we can pass to the B part of the domain. If you remember, this is the part where we have like a mixed sources of emissions. This is a GIF animated from the summer result, and now we have 3 points of comparison. And in this part, you can see that the model is doing in these 2 point observation. You have a positive bias, and if you are going to the south, this positive bias increase. So for the winter period, you can see that there is a lot of more the concentration are much higher than in the summer. So here now we have the same issue, where we have an overestimation, but it is more positively biased in this other zone. Now, for the last part of the domain, we have this. In this part of the domain, we have these rural sources. We have these 2 points of comparison in the summer period. The other point of comparison that didn't have values to compare. So in this case, we have this. In Valdivia, we have like a good agreement between the model and the observation, but in this final or like this extreme zone in the domain, we have a systematic positive bias from the model. And from the winter period, we have more data available. So in the winter period in this zone that we have a previous good agreement, now we have a negative bias in the model, but in the other points or the other cities, we have now a considerable positive bias from the model. As an overall result, now here you can see a scatter plot that shows in the y-axis the simulations, and in the x-axis the observation. And you can see that in the summer period, here we have the color coded the different domains that compare daily values between the simulation and observation. And as you can tell from the previous slide, we have a negative bias in the central part and a positive bias as you go into the south. The same happens in the winter period, and here's some detail that you wanted to see. That is the amount of the concentration that goes go up in the winter time. So in this case, we have the same problem, that is a negative bias in the north part and a positive bias in the south, but in this case the central part is negative too. Well, like I said, there is a systematic negative and positive bias depending on the location. So that is what we can say from this simulation. Here are some other results regarding the black carbon fraction. This is the summer 2-day simulation. As you can see, the brighter color or the darker color are the fraction of BC over PM2.5. In this case, the larger fractions come from all the cities in where the people is living. For example, there is Santiago and all other cities that is Temuco. But it's a low fraction in the summer. But in winter, this fraction increase in important way, and you can see how the fraction of BC is changing between the hours. So going to the emission level, we can say that this overestimation in the or this positive bias in the concentration are due to the PM2.5 emissions in the residential sector. So we can say that we have an upper level of emission in the residential sector, and also now we have to change these emissions to the other estimation that we have. This, for example, this graph shows the amount of PM2.5 emission from the NDC that also accounts for all. The major sector is the residential sector, but it's not that it don't have that strong participation. So we need to assure that if this level of emission represent a bottom level of the emission. So now we have to rerun the model and see how the result compare with the observation. So as a summary, we have this aerosol and black carbon simulation over the center and southern Chile, considering meteorological field at 10 por 10 kilometers resolution. In the result, which we can see a positive and a negative bias depending on the part of the domain that you are seeing. We attribute this overestimation in South Chile to large emissions coming from this residential sector. But also we have this negative bias in the central Chile that we need to take into account when we show the final result. So as a next step, we need to change the residential emissions to obtain another level, bottom or middle, we don't know yet, and validate this simulation against other satellite products like AAOD or and using this emission and concentration ratios in some part of the data you can see how the emission if one pollutant is overestimated is more overestimated than the other. So that is it. Thank you for your for listening me, and now I'm open to questions.
Thank you, Kevin. You did a lot of work, interesting comparison between simulation. Well, I will open for the question. We have one. Dalgisa, can you ask your question directly for Kevin?
Yes. Hi, Kevin. Good presentation.
Hi.
Thank you. I don't understand it. Okay, no. How you made the measurements of the percentage of black carbon in PM2.5? Because you show the result, but because this black carbon was obtained only by modeling, you don't have a measurement of the black carbon. I don't understand. Sorry.
Yeah, no problem. Probably it was my poorly English.
No, my English. Because here you have this result. This result is from modeling, or do you have some measurements of the black carbon?
Now, this fraction it shows that what is coming from the model. In the previous in the first part of the presentation, I said that when you put the emissions, you put a PM2.5 emission and such and others, and for the PM2.5 emission, the model make a fraction, have a fraction for the BC over PM2.5, or in this case, the EC, the elemental carbon. So the model calculate this share of EC and then have another share in the EC emission. That one is like an H emission and a new emission that come from that consider more how do you say this when the black carbon when is new emitted is more hydrophobic, but as is H is less hydrophobic. So that is one other fraction that the model do. But answering the first question, this is the fraction that come from the EC simulated over the PM2.5 simulated.
Okay, thank you.
And the next question, Fabio, can you ask
three questions? Therefore you don't have any measurement, black carbon measurement at ground level. Anyone? No one.
If we have some surface measurement, but it's only in the Santiago part. I'm not showing it here because we are focusing on get the best we wanted to first have a good level of PM2.5 emission and then compare it with the few observations that we have.
Okay. Second question is concerning the temperature comparison between model and observed. Can you go to the graph that shows the three places?
Yeah. Here.
Yes. Temperature. In Parque O'Higgins is really good.
Yeah.
But in Pá de las Casas and Oiahique, the minimum is not well represented. The maximum, yes. Not. Did you calculate the difference? How different they are from because it seems that it avoids the peaks from minimum and maximum. In average, maybe they are very close.
Are you asking if we compare the average value between both?
I think that
yes, because the average, the average seems very close. I and Rosie, we made this comparison between modeling and observe the data. It's not that bad. I can say that, or looking for a view.
But he is comparing in very complex terrain regions, and
that's what
he's showing the comparisons for each hour, the simulation and the data. It's it's very difficult to reproduce such details of the observation.
We are
anyway. It's good. Not bad. It's not bad. It's good.
It's not so bad. In my opinion,
the bias is not
modeling
working.
We have a good representation of the daily cycle that, like I said before, and this is an unfair comparison where you compare like hourly values, but if we compare like a daily average or something like that, we definitely have a much better result. I had this this comparison, but here I wanted to show this more unfair comparison.
Okay. No, not good. Not bad. And the third question is concerning, since the most problem that we have is residential black carbon emissions, there is any plan for the government to change this for normal heating system as Europe and United States use diesel or gas or similar, because they can produce pollution as well, but not as bad as coal.
Right. In Chile, we have this problem. It's not a new problem. We have I don't know how many years, but there is a lot of effort to change this with this attainment plan that is called in Spanish Planes de Descontaminación Atmosférica, in which there are several measures or mitigation measures that for the wood burning part you have this this renew of the house, where you improve their insulation, and also where you change this stove where the people heat their home. In this case, they are thinking on change on pellet. I don't know if that is the correct name in English, but you have this small compressed wood that you go into this stove, pellet stove, and the emission goes down. But it's difficult to change that because there is a lot of issue with that. Not only this is not a problem only of a technological matter. it's also a cultural problem, because the people want to wood to burn wood, just for like a traditional matter.
Oh, no, that's not good. Even or solar panels, or because you have lots of sun. In south, not that, but in
No.
central south, yeah, you
Yeah,
have
and
lots of wind or wind.
Yeah, like I'd say, is even if there is a lot of effort to solve this issue, but in the meantime we have this change in the stove, this improved house, and also there is an effort to implement this distrital heating that is also good for the houses. But even if you improve that the people in the south of Chile have a lot of issue with resources and problem with energy poverty, that they need much energy, much energy to heat their house. So even if you change that, even the insulation or change the stove, the people are burning a lot of wood to heat their homes.
Okay.
Okay,
Thank you.
Kevin, there is another question from Carla. She is asking what is the explanation because do you have a warm bias in the north and you have a cold bias in the south? He is asking if there is an explanation for this.
So if we have a warm bias in the south,
in the north,
yeah.
I think that she is referring to this part was north, and the next one, the next?
Yeah, this is in the winter. We have this.
No. Okay.
Yeah, these three are for winter
same.
period.
Yes, but the summer in the south part.
Yeah, I this in this part of this like a south location is in a really complex topography, where you have this city that is in the middle of a valley, and maybe the coarse grid of the model is capturing part of the hills that can contribute to this bias in the model, and to the north we have the different case, and maybe it can due to also this variability that comes from the low representation of this extreme that is happening in the city. This is a very urbanized territory in Parque O'Higgins. Is the like the middle point in this mega city that is Santiago.
Okay.
This slide is about the winter, not summer. Okay.
No, it's summer.
Yeah.
No?
Summer.
Yeah.
No, this is winter. The previous
winter,
one,
because the temperature is lower. Here is summer. Yes.
Yeah,
because the value of the temperature. Yes. The next is winter.
Yeah.
Because there in the title is summer.
Yeah, but that is an error from my part. But here in the bottom part you can see the dates. That is winter, and that is summer. Okay. Sorry for that.
Well, there are some comments here. Alejandro. Adalgisa is comment that here in Brazil are...
the name of the wood, the compact wood here in Brazil that are using in pizzerias. Alejandro talked that it's not only in south of Brazil, we have some residents all in northeast that use I don't know, nowadays with our crisis, maybe many people using wood for cooking. But here in São Paulo, we have the pizzerias, yes, that use wood for our good dinner in the weekends.
Okay, and this is a comment of Alejandro. Alejandro is commenting that I think the problem of bias could be explained about the spatial resolution.
Yeah, I agree with that. We have a course grid, but since this study is only the aim of this study is to get like the best level of emission. We don't want to reproduce the exact variability in an exact point. We need a level of emission or a range of emissions.
Okay, no more question, please. Sergio is commenting that muy buena presentation.
Gracias, Sergio.
Felicitations. Felicitaciones.
Gracias.
Bueno, well, if there is no more question, I will close the seminar now. Okay. Thank you, Kevin, for your presentation, for your contribution with our seminar. See you.
Thank you.
Muchas gracias.
Na próxima semana tem mais seminário, hein? A Márcia que está organizando e ela já divulgou e vai continuar divulgando novamente.
Thank you very much. I'm glad that you enjoyed that.
Sucesso.
Hasta la vista.
I hope you do have a success in your PhD.
Gracias, Kevin. Muy buena presentación, tus animaciones, excelente, me encantó, estoy fascinado. Felicitaciones, hermano, un gran abrazo.
Gracias. Take care. Bye.
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 See you.
Oi, Rose, se der, vamos ver se a gente consegue conversar mais tarde.
Tá, eu tô aqui.